Hello guys, and welcome back to another episode of chemistry. And of course, in this episode, we're going to be looking at stereoisomerism. Stereoisomerism. All right, and then of course, we know that stereoisomerism is divided into two. We'll talk about what geometric isomers, geometric isomerism, and optical isomerism. All right, so before we continue our study of geometric isomers, let us first of all look at some questions from the O3 School JAMB app. Please do know that this tutorial is brought to you by the O3 School JAMB app. But before we talk about the app, let's see a question from the application. This is a 2023 question. 2023 question number 6. And it says, which type of isomerism is exhibited by molecules that have the same molecular formula but differ in the spatial arrangement of their atoms? Okay, A, it says structural isomerism. B, say geometric isomerism. Of course, the question is being displayed on the screen right now. C, optical isomerism. D, functional group isomerism. I'm going to come back to this question and many more questions at the end of the class and not before. So please make sure you stay to learn first before you jump into answering questions, so that you have a vast understanding about what the topic in question. So we said that was stereoisomerism divided into geometric isomerism and optical isomerism. And of course, we said that was stereoisomers have the same molecular formula, but they differ in their orientation, that is in the arrangement of their atoms in space, in the spatial arrangement of their atoms in space. That is the difference when it comes to isomer. And we say it's divided into geometric isomers and optical isomers. So in this class only, I'm going to be looking at geometric isomers. In the next class, we're going to look at optical isomerism, so that we do not bore you too much. All right. So now, what are geometric isomers? All right, geometric isomers are isomers that have the same molecular formula, but they differ in their orientation, and the difference in their orientation is due to the rigidity of some certain structures. Okay, we said that the difference in their orientation, that is the arrangement of their atoms in space, is due to rigidity. Is due to rigidity of some certain structures. Rigidity of some certain structures. Certain structures which are organic. These structures are talking about, the rigidity of these certain structures we are talking about are these structures are organic. They're usually organic. Most especially those containing carbon to carbon double bond. All right, so we say that for geometric isomers, all right, the difference in their orientation, okay, is due to the rigidity of some certain structures. Those structures are organic. They are organic, especially those containing carbon to carbon double bond. You must take note of that. Now, geometric isomers are divided into two. All right, we have the cis isomers. We have the cis geometric isomer, cis, CIS. Divided into two, we have the cis geometric isomers. Then we have the trans geometric isomers. All right, so geometric isomers are divided into two: the cis and the trans. The cis and the trans. Take note of that. Very, very easy. Now, what are the cis and the trans isomers? How would you describe them to someone? Someone asks you, what is a cis geometric isomer? What will you say to the person? How will you describe it? All right. If somebody asks you, what is a trans geometric isomer? How will you describe it to the person? All right. So it's easy. Please take note of this. Cis geometric isomers are those isomers that have two groups on the same side. Okay, for cis, they have two groups on the same side. Okay, cis geometric isomers have two groups on the same side. Why trans have two groups on different sides. On different what sides. Okay, please take note of that. Cis geometric isomers have what? Two groups on the same side, while what? Trans geometric isomers have two groups on different what sides. All right, so please take note of that. So let us see an example. So if you have what? Carbon double bonded to what? To carbon, and then here we have what? Chlorine. Here we have what? Chlorine. Here we have what? Hydrogen. Here we have what? Hydrogen. All right. This is a what? This is a cis geometric isomer. This is a cis isomer. This is cis. C-I-S. Cis isomer. All right. Because it has what? Two groups on the same side. You can see chlorine here. You can see chlorine here. All right. You can see hydrogen here. You can see what? Hydrogen here. Now for the trans. Okay. For the trans isomer, we are going to have carbon double bonded to carbon. All right. Here we are going to have chlorine. Here we are going to have what? Hydrogen. Here I'm going to have what? Chlorine. Here I'm going to have what? Hydrogen. All right. So this is what? This is trans on the other hand. This is a trans isomer because it has what? Two groups on different sides of the carbon to carbon double bond. This one has two groups on the same side of the carbon to carbon double what? Bond. Please take note of that and note it. It's very, very easy. Okay. So this cis and the trans isomers, all right, of the type of geometric isomers we are discussing, they have what we call they are different. They have different physical properties. They are not the same. All right. They have different physical properties. These cis and trans isomers have different physical properties. And it is the properties we are going to work looking at right now. All right. So now, let us begin with the fact that this cis geometric isomer or this cis isomer has what? A dipole moment of 3 dBi. Okay. Know what dipole moment is, right? D-I-P-O-L-E. Dipole moment. Okay. Dipole moment is the measurement of the separation of what? Of two opposite charges. Okay, that is dipole moment. Is the measurement of the separation of two opposite charges. Okay, so cis isomers have what? A dipole moment of 3 dBi. Mu is what did I write it down? Just right now. Mu is what? Is 3D. That is what the dipole moment for cis isomer. For this cis isomer we're looking at here. Okay, so we're trying to tell that they have what? Different dipole moments. Okay, but for the trans has what? A dipole moment of what? Of 0. All right, trans has a dipole moment of what? Of 0. The unit of dipole moment is dBi. Is dBi. It's spelled like this: D-E-B-Y-E. dBi. dBi. Okay, so cis isomers has a dipole moment of what? Of 3D, while the trans isomer has a dipole moment of what? Of 0. All right, so if you draw their dipole moment, for example, let me draw this out so that it becomes very clear. If you draw the dipole moments, okay, on these structures, you will see what I'm talking about. For example, for this cis isomer now, for this cis isomer, we have chlorine here. If you draw the dipole moment, the arrow will be pointing to the more electronegative elements. Okay, the arrow will be pointing to the more electronegative elements. For this one, the arrow will be pointing to this direction. This is how we draw what? Dipole moment. Okay, this is how we draw the arrow. See this arrow with this cross here. Then of course we can draw the dipole moment for the trans isomer also. Okay, so we have carbon double bonded to carbon. Then here we have chlorine. Here we have what? Hydrogen. Here we have what? Hydrogen. Here we have what? Chlorine. Okay, so the arrow also will be pointing to chlorine, to the more electronegative what? Element or atom. Then of course the arrow also will be pointing what? To chlorine here also, the more electronegative what? Atom. So if you look for this trans isomer, this is trans, this is cis. For this trans isomer, if you look at it very clearly, you see that this arrow is what? Is going this way, while this other arrow is what? Is coming what? Down. All right, so because they're going in opposite direction, the arrows what? We cancel out. That's why we say that what? That the dipole moment here, mu, is what? Is 0 what? D, right? That is 0 dBi. Okay, but for this one, for this case, this arrow is going up, this other arrow is also going up. So there will be a net dipole moment. That is what? That is still also what? Going what? Up. So we can add the what? The vectors. We can add the two vectors. And then we're going to have a net dipole moment that is going what? Up. It's as simple as ABC. All right, so the dipole moment for what? For the cis isomer is 3 dBi, while the dipole moment for the what? For the trans isomer is what? 0 dBi. And that is why we say, because what this dipole moment, we can have a net dipole moment. All right, that's why we say that this cis isomer is polar. We say it is what? It is polar. It is a polar molecule. All right, while this trans isomer is what? Is non-polar. All right, so that brings us to another what? Physical property we are distinguishing between the cis isomer and the trans isomer. The cis isomer is what? Is polar, while what? The trans isomer is what? Is non-polar. The trans isomer is non-polar, the cis isomer is what? Is polar. Also, the boiling point for what? For the cis isomer here is what? It's around 60 degrees Celsius. Okay, it's around 60 degrees Celsius. Why the what? Why the boiling point for this what? Trans isomer is around 47.5 degrees Celsius. Okay, before we will talk about this, know that what? Generally in chemistry, polar molecules have a higher boiling point than non-polar molecules. Please take note of that. Polar molecules have a higher boiling point than non-polar molecules. Please take note of that. So if you can see very clearly, you can see that what? The cis isomer and the trans isomer have what? Different physical properties. They have different physical what? Properties. All right, and that's why you are seeing that what? Their properties here, that what? They're all what? Different. Also, it is not just easy for you to convert a trans isomer back to a cis isomer, or it is not easy for you to convert a cis isomer to a trans isomer, because the energy barrier between what? The cis isomer and the trans isomer is very, very high. The energy barrier is very, very what? High. Take note of that. So it is not easy at all. There's no free rotation because of this carbon to carbon double bond. There is no free rotation. All right, so you cannot easily convert you cannot easily change this chlorine to what? This hydrogen here to what? To chlorine, so that it becomes what? A cis isomer. It is not what? Easy. It's not something you can easily do because there's a high energy barrier. The carbon to carbon double bond does not allow for free rotation. For you to be able to convert from a trans isomer, from this one to what? To this cis isomer, you need to first of all break the pi bond that is present in this carbon to carbon double bond. Okay, I've talked about what? If I have not been following all our episodes on organic chemistry, you are doing yourself. So please go from the beginning and follow us up till now, and then you will see that what? You are doing yourself a great deal. Also get the O3 School JAMB app. The O3 School JAMB app has all you need to succeed in your examination, has all the past questions you can ever want to need in this life, and also has some interesting features designed to make you succeed in your examination. Go and look at all our testimonies. You will also know why you should get that app immediately. Has all the past question. There's a question search feature where you can search for question according to topic. There's also a UTME mock challenge that you can participate in every Saturday with your mates. You compete with your mates, get used to JAMB past question, and of course you build confidence towards the main exam. Activation is just for a little fee. So please grab that app immediately. Go to Play Store, download it immediately, and start practicing vigorously like your life depends on it, and you will see that what? You are successful in the end. All right, so please get the application immediately. Okay, so that is what the cis and the trans isomer. Like I was saying, the cis isomer also, this because of this carbon to carbon double bond, it does not allow for what? For free rotation. That is why you cannot easily convert a trans isomer to a cis isomer, or from a cis isomer to what? A trans isomer. Now, in another news, okay, let's look at ethane. Ethane has two forms. Ethane has what? Two forms. We have what we call the staggered form and the eclipse form. Okay, ethane that you know, ethane is an alkane. Okay, ethane is an alkane. That is what? C2H6. This is ethane drawn like this. It's a single bond. All right. Okay, H. Okay, this ethane that we're talking about, it has two conformations. We have what we call the eclipse conformation or the eclipse form, and they also have what we call the staggered form. the staggered form. Okay, so I'm showing you the eclipse form right now. All right, that is the eclipse form, and then I'm showing you what the staggered form right now. So there are two forms of what? Of what? Of ethane. That is ethane, or ethane as you may call it. Okay, that is ethane. All right, so it has to form the eclipse form and the staggered form. Okay, but this carbon to carbon single bond here, all right, the carbon to carbon single bond here, all right, it has free rotation. It has what? Free rotation, unlike what? The cis what? Isomers and what? And the trans isomer. Okay, so you can easily convert from the eclipse form to the staggered form. Okay, the energy barrier between these two forms is not very, very high. Okay, the energy barrier between the eclipse and the staggered form in an ethane molecule is what? It's around 12 kilojoule per mole. So the energy barrier is what? Is very, very low. It's very, very low. That's why you can be able to convert from the eclipse form to the staggered form, and from the staggered form to the eclipse form, as vice versa as you may want it. Okay, but it is not like that in what? In this cis and trans isomer, right? Because the energy barrier between them is what? Is very, very high. So please take note of what? Of that. All right. So just to, in addition to this, before we start answering questions from the O3 Schools JAMB app, all right, before we start answering questions, also, let me just add one or more to it. You can also represent what? Cis and trans isomers in what? In a ring system, or in ring form, ring, R-O-I-N-G, in ring form, okay, or in a ring or system. Let me show you an example, okay? So you can also what? Write what? A cis, or showed cis and trans isomerism like this. Can have like this, okay? This is chlorine. This is chlorine, okay? This is what? This is the cis form, okay? Then we can also have what? Something like this coming down like this. This is chlorine. This is chlorine. This is what? The trans form, okay? So this is the cis isomer. This is what? The trans what? Isomer, all right? So this is what? A ring system. Also, you can also represent it in another way, all right? Using what? Ring system. Okay, you can represent it like this. This way, all right? Then you have what? Okay, you can see the arrow. This arrow is what is going out of the page. Okay, you can represent it with what? With what? Two hydroxyl groups. Okay, and then this one also going out of the page. All right. All right, this is what? OH also. This is what? This is the cis isomer. Okay, and then this is what? The trans isomer. Also have something like this. Okay, in this case, we're having what? This one going into what? Into the page, all right, and this one is going what? Out of the page, all right, like this. Okay, so I'm going to have two hydroxyl groups. Okay, one going in out of the page, one going out. So this one is what? Is the trans isomer. All right, so please, you can take note of this. So there are so many other ways. You can also represent them what in they also find in trihydric alcohols and glycols and so on, what and so forth. All right, so please take note of this. This is what? Geometric what? Isomer. Okay, we have the cis and the trans isomer. That's what I said. We say the cis isomers have two groups on the same side, while the trans isomers have two groups on what? On opposite sides. All right, so please, I'm going to go to the O3 School JAMB app immediately, and then we answer what? A question from it, so that we can what? Get what? An overview of how JAMB can set questions. Okay, let's go to the application. Like I said, please go and get your O3 School JAMB app immediately. Get it immediately and start practicing your way to success. In the next class, we're going to be looking at optical isomerism. Let's see. 2023 number 6, it says, which type of isomerism is exhibited by molecules that have the same molecular formula but differ in the spatial arrangement of their atoms? The question is being displayed on your screen right now. A said structural isomerism, that is not it. B, they say geometric isomerism. C, optical isomerism. D, functional group isomerism. The correct answer there is what? Is option B. Okay, they have what? The same molecular formula, all right? But the difference in their orientation is due to the rigidity of some certain what structures, which are what? Organic, especially those what containing carbon to carbon double bond. All right, so that is what geometric what? Isomerism. Now let us see another question. This is a 2021 question. 2021 number 9. All right, it says, okay, you are seeing the structure on the board. The first one and the second one. They say they are, okay, let me draw them on the board. So we have what? C, double bonded to what? To C. We have what? Bromine. Then here we have what? Hydrogen. Then here we have what? Bromine. Then here we have what? Hydrogen. Then the second structure, carbon bonded to carbon, double bonded to carbon. Here we have what? Hydrogen. Here we have what? Hydrogen. Here we have what? Bromine. Here we have what? Bromine. Okay, they say they are what? A, they say allotropes. B, they say dimers. C, they say polymers. D, they say geometric isomers. What are they? These are what? Geometric isomers. And of course, they are the cis and the trans form. Which one is the cis form? This is the cis isomer. Okay, and then this one here is what? It is trans isomer. Okay, so there are so many other questions on this application. Using the question search feature, you can what? Search for question based on a particular topic we just studied. You can answer question on that topic to build your confidence. All right, so that any question that come under that topic, you will match it on the ground like machala. All right, so please, my name remains Owolabi, thank God, your grand commander. I will see you in the next episode where we'll start talking about optical isomerism. Thank you for watching. See you in that class.